Okay, right. Thank you everyone for coming to this UK SPIS seminar. This is the first one after the Easter break, actually. And today it's our great pleasure to have Kenny Paterson here to give us the talk. I think I don't need to say too much about Kenny. Everyone know Kenny already, right? He was a professor at Royal Holloway, and then he moved to ETH Zurich in 2019 to lead applied cryptography group. And today, he's going to talk about probabilistic data structures in adversarial environments. Now I pass the stage to you, Kenny.
Great, thank you very much, Changyu, for the introduction and the invitation to come and speak today. Just check everybody can hear me okay, so maybe give me a thumbs up, Changyu, if you can hear me fine.
Yeah, I can hear you.
Oh, good, excellent, thank you very much. Here is an overview of the talk I wanted to give today. First, I'll introduce probabilistic data structures and talk about how they are used and how they're increasingly being used in situations where there might be an adversary wanting to influence the setting. Then I'm going to look at two different foci, one on something called HyperLogLog, which is a cardinality estimator. And then the second focus will be on approximate membership query probabilistic data structures, or AMQ PDS. Here, you can think of Bloom filters as your canonical example of an AMQ PDS, if you've heard of Bloom filters before. And then I'll have some closing remarks at the end. And as we said, feel free to interrupt on the way through. If you raise hands, I should get an indication here that you've done that. Otherwise, just interject into the audio stream if you want to ask a question. So what are probabilistic data structures? Well, they're very useful tools when it comes to analyzing large amounts of data, particularly large data volumes. We live in a world of big data and so on. And so what we typically want to do is do things like estimate the number of elements in a set. We want to estimate the different frequencies of elements in sets and so on. And we are willing to sacrifice perfect correctness for efficiency. So perfect correctness would mean that no matter what answer we output in response to some kind of query about our data, the response would be perfectly correct. Typically, it's very, very expensive to achieve perfect correctness in terms of, say, memory or computation. So we'll do some kind of approximation. And those approximations are often good enough in practice. These are becoming more widely used in practice, these probabilistic data structures. They're very well worth learning about, because your Google interview, when you interview there for a job at Google, will certainly ask you about, say, Bloom filters. It's kind of a typical thing that Google care about, and that gives you a sense of where they might be used. Also, a very vibrant area of research in computer science, in theoretical computer science. There are very beautiful ideas involved here, lots of different interesting mathematical tools being used in the analysis. But the results that we have in computer science for the performance of these probabilistic data structures are usually focused on the average case performance, where, say, the inputs that are being processed are chosen uniformly at random from some set, and there's no adversarial influence over the choice of values that are being processed. So where are we in theoretical computer science, just to get a handle on it? So I took this from the ACM classification of subjects in computer science. So we're within the theory of computation, design and analysis of algorithms as a subtopic, and then data structures, design and analysis as a subtopic of theory of computation. And down here you see Bloom filters and hashing, sketching and sampling, and so on. So this is the kind of area that we're working in. Indeed, there are sort of, if you go to the conference Principles of Distributed Computing, PODC, you will find lots of papers about probabilistic data structures and their analysis. So this is a very nice and well-founded branch of computer science, as well as being useful in practice. There have been lots of application-specific innovations. So, for example, Bloom filters were introduced in 1970, but recently people started looking at Bloom filter cascades to enable perfectly correct set membership testing, for example. There's a lot of designs to choose from. If you browse through the pages of PODC, you'll find dozens and dozens of different solutions to every problem, with different trade-offs between memory and computation, lots of optimality results, and lots more PDS being invented every year. But there's actually a practice and theory divide, much like in cryptography. For example, HyperLogLog is a cardinality estimator, which we'll talk about in a lot of detail in the slides ahead. It's not optimal, but it performs very well in practice. On the other hand, if you there's a paper by Kane et al. From 2010, just a few years later, that gives the optimal solution to the problem of cardinality estimation or approximate cardinality estimation in terms of the storage required and the accuracy that can be achieved in terms of cardinality estimation. But as far as I know, the solutions pointed out in KNW are not applied anywhere. There's no implementation of them, for example. So this is something we see a lot in cryptography, where we know that we can do RSA encryption using PKCS #1 version 1.5, and we might be vulnerable to Bleichenbachers attack, or we could use some RSA OAP which has provable in CCA security. We have good theoretical solutions, but in the real world, people are still using things that are vulnerable to attack. So this divide exists here, just as it does in cryptography. Okay, so the issue I want to highlight here is that the ubiquitous nature of these probabilistic data structures, or the increasing ubiquity, implies a potential for abuse, because PDS are now being deployed in adversarial settings, where rather than in the average case setting where the analysis is usually done. And so the gap between average case and worst case performance can be used to adversarial advantage. You can make bad things happen as an adversary. So the thesis of this talk, the overall thesis of the talk, is that we should really revisit PDS using a cryptographic mindset. And if we do so, we will gain. We will end up with better solutions, more robust solutions that are more broadly applicable, including in the case where we might have an adversary present who's trying to manipulate the data structure. So what this involves, this kind of approach to thinking about PDS from a cryptographic mindset, is first of all, find out where PDS are being used beyond their original design envelope, beyond their original design parameters. That means reading blogs and looking at source code in data processing systems and so on. So get a good snapshot of what's going on out there in the world. Develop attacks in these adversarial settings. So understanding where they're being used and where they might be misused, and then understand to what extent can they be abused in those settings. And then also thinking about defenses. So how can we defend probabilistic data structures against attacks? How can we formally model attacks and then actually prove something about the security of probabilistic data structures, prove something positive about their security, and also understand the cost of making probabilistic data structures secure. Do we need to introduce expensive cryptographic operations, or can we do it just by using something like keyed hash functions? So that's the kind of approach that I'd like to put forward as an interesting way of researching in this space. And of course, it's inspired by how we do cryptographic research, quite obviously. So what I want to present today are two case studies. The first one, we'll talk about HyperLogLog and how to use it to do approximate counting and analyze its security. And then in much less detail, I'll talk about approximate membership queries using Bloom filters and cuckoo filters, how those can be attacked and also how those can be secured. But I'm really going to spend a lot more time talking about the first one, since it's the one where we've done a lot more work to develop the story. So let's start by talking about HyperLogLog, and I'll give you a puzzle to solve. And here, maybe some of you we'll have some ideas about how to solve this puzzle, so please do feel free to answer the question. So I give you a small amount of memory, and I want you to estimate the number of distinct items in a very large collection of items. Say, let's call that large collection of items X. And let's assume that each item in the collection is presented to you one at a time as a data stream. So it goes past your analysis tool, and you're able to look at it for a short space of time, and then you have to move on to the next one. So the data stream itself is much too large, or the set X of items is much too large to store. There might be lots of repetitions within the set X, and you want to estimate how many distinct items are there that you have seen in your data stream. So this is the problem of cardinality estimation. Of course, you might want to do this exactly, but to do it exactly would require a large amount of memory, right? You'd have to store a complete list of all the data items that you've seen in your data stream. For each new data item, check whether it's in your list or not, and then update your list accordingly if it's a new item. So that would require a lot of storage, a lot of memory, and so it's not really feasible to do for very large data sets to do exact cardinality computation. So a question for you: how might you go about solving this problem approximately? Any ideas? Just see if any hands go up. I don't see any. So maybe in that case, I will just move on to tell you how it can be done. So here's a solution. Suppose we have a hash function h, which maps our set x onto n-bit strings. And let's suppose that h has some suitable uniformity property. Let's suppose it's, oh, sorry, I do see solutions in the chat, right? So Siamak says a hash plus a Bloom filter, and Roberto says you can divide and conquer maybe. So interesting thinking about using a Bloom filter. It turns out the size of a Bloom filter is actually larger if you want reasonable false positive probability. The size of a Bloom filter has to be larger than the size of the set x that you are trying to count. So they're rather larger than the number of distinct items in x. So Bloom filters are actually expanding in a sense, which is something that's maybe not that well understood when people use Bloom filters. So I'm going to show you a different solution, which does use hash functions. So CMX along the right lines here. So we have our hash function h, and let's suppose that its outputs are, approximately uniform. We can be more precise about this if we need to be, but we're just talking informally for now. So let's take each item x as it arrives. Let's compute its hash value, and let's look at the bits of the hash value. So we have n bits in the hash output, and let's look at the position of the leftmost 1 bit in the bit representation of hash of x. And let's call the maximum index that we see across all of the values x, let's call that big M. So just to make this clear, suppose our data stream consists of animals, and suppose we hash dog and we get this little 8-bit string here. We see a 1 in the leftmost position 1. So we would set M to equal 1 from after processing the first item in our data stream. Then along comes the second item, cat, and we see that now this begins with 0, 1. So we see now that we have a 1 in the second position. So we would increase M from M equals 1 to M equals 2, because we now have a 1 bit, the first 1 bit that's further to the right than the previous maximum that we saw. Then we hash fox, and it begins 1, 1. So here we would not increase M because the position of the 1 bit is in position 1. And we already saw a first 1 bit in position 2 in the previous example, the previous animal that we hashed. So here we would stick with M equals 2. And finally, we hash pig, and we get 0, 0, 0, 1, 0, 0, 1, 0. This is just, hypothetically for some hash function. And so now we would increase M to 4 because the position of the first 1 bit in pig is 0, 0, 0, 1. So all we're doing is keeping track of the longest string of zeros that we saw at the beginning of one of our hash outputs. And then as our cardinality estimate, we would just take 2 to the power of m, where m is that maximum that we saw across all of our values. Okay, so this gives us a cardinality estimate that's always a power of 2. So it's not going to be necessarily always very accurate. I mean, so here, for example, we had 4 items, and our cardinality estimate ended up being 16. And obviously, in this case, the small example, the cardinality estimate is way too large. However, it turns out that this is not a bad cardinality estimator. So the intuition for this being good is that if we have about 2 to the m distinct values x, we would expect to see this length m string beginning with m minus 1 zeros followed by a 1 as a prefix of some h of x about once. So if you think that the values x are random, or the hash function behaves as a random oracle, then after about 2 to the m values, you would expect to see this string once. And so then keeping track of the length of the number of 0 bits you've seen is a good indicator of the cardinality of the set that you've been processing. Let's see, is there a question? Oh, Orpheus in the chat says, genius. Indeed, it's a very, very clever idea. And what's very nice about it is that the storage that you require is only logarithmic in the value m. And actually then it's log in 2 to the m, where 2 to the m is the approximate size of the set that you're processing. And this is why it's called HyperLogLog, the estimator that I'm going to show you, because it requires only log bits to represent the cardinality of a set. So this estimator, you can prove that it's statistically unbiased, but it's not very accurate on its own. So the trick is to use this kind of estimator over and over again. So what we do is we combine many simple but independent estimators to improve the accuracy. That's the core idea of HyperLogLog. So what we'll do is use the leftmost n bits for some parameter n of the hash value to determine which one of 2 to the n different estimators to update. And then we'll use the rightmost bits of the hash value to determine how to update that estimator, just as we did before. So we'll look at the position of the first one in the rightmost bits of h of x and use that to decide whether or not to update a counter for indicated by the first n bits. So we're going to have 2 to the n different counters, and each of them is going to be rather small. And then we're somehow going to combine all of those estimates together to get a final estimate for our cardinality. So we take an average across the different estimators. Okay, so that brings me then to actually give you the full and detailed definition of the HyperLogLog cardinality estimator from the original paper by Flajolet et al., who introduced it back in 2007. So we have our hash function mapping from our input domain to 32-bit strings. So the original version of HyperLogLog just used 32-bit outputs. And this is to do with the fact that they were designing for sets of some maximum size around about 2 to the 32. So in modern applications, you might use a hash function with a 64-bit output to enable you to deal with much larger sets. Then we introduce this notation rho of s, which tells us the position of the leftmost 1 bit of the input. So for example, row of 1 followed by some bits is 1, row of 0, 0, 0, 1 followed by some other bits is 4. Okay, so this is the function that we're using to track the position of the leftmost 1 bit. Then we'll take m equals 2 to the n, where n lies between 4 and 16. So m is going to be the number of estimators that we're going to combine, or the number of buckets that we have in our HyperLogLog estimator. And then we have some constants. These constants don't matter too much. All you need to know is that they converge towards something like 0.72. And this constant is just going to be used as a corrector to correct the cardinality estimate. Okay, so how do we actually form our estimates? So for each element in our set X, we hash it first of all to get a value Y. We take the first n bits of Y and turn it into an integer and use that to give us an index J. So this is telling us which of the 2 to the n different estimators we're going to update, okay? Or it gives us what's called a bucket index. So our estimator consists of m registers or buckets labeled m1 up to mm, and they're all initialized to 0. So here, by hashing X and looking at the first bits, we've identified a bucket that we want to use to work with for this particular value X. And now we take the remaining L bits of our hash value. So we take the rightmost L bits and we calculate the row function on the bit string W. So we say, where is the first 1 bit starting from yn plus 1? Okay, so this might begin 0, 0, 1, in which case we would set row of W to be 3. And then we update m of j, the counter that we're keeping in the jth bucket. We take the maximum of the existing value in the bucket and the value of row of W that we just computed. So that's just implementing that idea where we only update the counter if it's larger than the previous seen value. So that's why we have a max here. Okay, so at the end of this process, this gives us a whole bunch of buckets. Each bucket contains a number, and we want to somehow combine those numbers to make our cardinality estimate. And so the raw HyperLogLog estimate is produced by taking this rather strange average. So we take the sum over all the buckets, 1 up to m, of 2 to the minus contents of the bucket, 2 to the minus mj. So that's a sum of powers of 2 to negative numbers. Then we take the inverse of that, and then we multiply by the square of the number of buckets times this correcting constant alpha m. And so this maybe is a little bit counterintuitive at first, But what Flajolet and his co-author showed is that this gives you a rather good estimate in a certain range, in a certain for a certain size of the set X that we're working with. It gives you an unbiased estimator with a small error by doing this particular combination of the individual bucket contents. Okay, so that's not quite the end of the story for HyperLogLog. I want to actually now show you, sorry, I just have to deal with some windows popping up. There we go. Show you actually what we do next. So we actually don't necessarily work with this raw cardinality estimate directly. The HyperLogLog specification says, well, if the estimate is small, if it's less than 2.5 times the number of buckets, that's what this is saying here. If the estimate that you got from this process was small, then replace it with some other kind of estimate altogether. Look at the number of registers that are still empty and use some logarithmic formula to correct in that range. So this is called a small range correction. So our estimate is small, and it turns out that for very small numbers or very small cardinality estimates, the raw cardinality estimate isn't very good. And this is a better estimate. This is a kind of a hit count estimate for the cardinality. In the middle, if the estimate's not too large, if it's less than or equal 1/30th of 2 to the 32, then we use the raw estimate directly. And otherwise, if it's very large, we do a different kind of correction. We take the raw estimate, and then we do some other logarithmic correction. And this is really accounting for the fact that with very, very large cardinalities, you're going to get lots of collisions in the hash function. And so you're not really going to be accurately counting any longer. So we want to do some kind of logarithmic correction in this large range setting. And what Flajolet et al. Show is that the typical relative error of this estimator is growing as 1 over the square root of the number of buckets. And it's like some kind of constant divided by the square root of the number of buckets. So by increasing the number of buckets or the number of registers you use, you can make these estimates more and more accurate. Okay, so before I move on, does anybody have any questions about how HyperLogLog is operating, what it's actually doing? Feel free to unmute yourself and just ask a question if you have one, or you can ask in the chat if you have a question.
Why is the n chosen between 4 and 16 always?
Oh, okay. I think the volume is very quiet on that question, but I think the question is, why is m chosen between 4 and 16? So indeed, you could use larger values of n, but in the original paper, they only considered up to 2 to the 16 buckets. And I guess the idea is the more buckets you use, the more memory you have to dedicate to this. And so the whole point of this is to minimize the amount of memory required to get an accurate estimate of the cardinality. So you could indeed go further, but then you would be using more RAM to store everything.
Yeah, I see. Okay, thank you.
Okay, good, thanks for the question. Okay, if there are no more questions, then let's talk about how HyperLogLog is being used in the real world. So it's actually being increasingly used in real world applications, including some where the inputs might be adversarially chosen. So there's a number of research papers that say we can use HyperLogLog to count the number of distinct ports that are being accessed on a particular server on our network. And if that number becomes very large, then you might say, there's a port scan attack underway, and now I should limit the traffic in my network, for example. So you can use HyperLogLog as a quick and dirty way of tracking, of estimating whether there is a port scanning attack underway or not. Similarly, in networking applications, you can use it to count the number of distinct network flows in your network, so the number of distinct TCP connections based on source ports and destination ports and IP addresses, and use those results to do congestion control, to reroute traffic around points of congestion in the network, for example. The third example is actually Facebook published a very interesting blog where they explained how they use HyperLogLog to count the number of unique Facebook users who are logging in during some time interval. So each Facebook user, of whom there are billions, has a unique ID, and then that ID is hashed, and that ID is used as the input to the HyperLogLog estimator. So clearly, in all three cases here, there is adversarial incentive. So for example, an attacker might want to evade a port scan by sending many packets with different ports in the packets, but choosing them in such a way as to fool the HyperLogLog estimator into thinking that it's not actually seeing many different values, when in reality, the attacker is carrying out its port scan as usual. Okay, a denial of service attacker might want to create a lot of traffic in the network, but fool the detector into thinking that there are not many distinct network flows, because by fooling the HyperLogLog estimator into underestimating the number of distinct network flows there are in the network. And similarly for Facebook users, here it's a little bit more esoteric, but maybe an advertiser might want to inflate the number of unique Facebook users, and then potentially claim that they're not getting the advertising revenue they should get, for example. So that third scenario is a little bit more far-fetched, but the first two are definitely realistic for these systems that are using HyperLogLog to detect network attacks. So actually, HyperLogLog is also very widely implemented. So there are lots of tools out there for doing large-scale data processing. So I mentioned Redis, it's very popular. There's also Google BigQuery, Apache Spark, and Druid, and so on. And all of them are implementing HLL, and they're actually almost all implementing it directly from the research paper, as I've described it up to this point. So what I want to show you is that HyperLogLog can be exponentially bad in doing cardinality estimation in adversarial settings. And we're going to focus on making HyperLogLog undercount the number of distinct items in a set rather than overcount, but everything I'm saying can also be adapted to the overcounting case. And this is joint work with Mathilde Raynal, who is now a PhD student at EPFL, but was previously a visiting master's student at ETH. The paper that describes this work is to appear at Euro S&P 2022. And if you're interested in taking a look, we've had a preprint online for quite a while now, since late 2021. So what we do in this paper is we first of all break HyperLogLog, and then we show how to repair it. So by breaking it, what I mean is we show how to do cardinality manipulation attacks via what we call input selection. So this basically means the adversary carefully selects which inputs it adds in its data stream in such a way as to force the HyperLogLog estimator to massively undercount the number of elements in the set. Then we build a security model, and it's a simulation-based security model to study this kind of attack. And finally, we show how to provably protect HyperLogLog against cardinality manipulation at low cost, basically by replacing the hash functions with a pseudo-random function, and then analyzing the result in this simulation-based security model. So let's start by looking at cardinality manipulation attacks via input selection. Here, the core idea is that we assume the adversary knows the hash function h, and is actually able to exert some kind of control over which values x are going to be inserted into the instance of HyperLogLog. Why does that make sense? Well, think about that network adversary we were talking about before, the one doing the port scanning. Maybe the adversary can control certain fields in the IP header, for example, the ID field, and has complete freedom to choose the port, but by controlling the ID field, has some control over which values are going to be inserted into the instance. So the adversary is only going to need a little bit of flexibility in our attacks in order to be able to distort the cardinality estimation. And then the idea is that the adversary can just look at the bits of h of x for each item x, and then just insert the ones which begin with few 0 bits, maybe no 0 bits or 1 0 bit. And the effect of that will be to keep all the bucket values small in the HyperLogLog buckets. And what that also means is that if all of those values are small in the buckets, then the raw HyperLogLog estimator will also be small, even though many items were inserted. And that's maybe not so easy to see, but let's go back very briefly and look at the algorithm for computing the raw HyperLogLog estimate. What I'm saying is the adversary can keep these m of j's small. So these powers here will be relatively large numbers that we're adding up, and then we take the inverse. So we end up with a small number in this term here, which is then multiplied by alpha m times m squared. So overall, we can make the estimate remain small. Okay, so just by carefully choosing which values to insert, we can cause the cardinality estimation to be really lower than it should be. Now, here I made the assumption that we know the hash function that's being used. This is a reasonable assumption in most cases because almost in fact, every single implementation of HyperLogLog that we looked at, used a fixed hash function h, which you could read out of the source code. So knowing the hash function is a perfectly realistic assumption, but you might say, well, can I still do attacks if I don't know the hash function? Can we find even better attacks than this simple selection of values to control the value of the hash function or the number of leading 0 bits in the hash function? Does it help if the attacker has access to the actual cardinality estimates themselves during the course of the attack? So what if we give the attacker an API that enables it to interact with the HyperLogLog cardinality estimator? Or can we even consider a model where the adversary is able to corrupt the HyperLogLog instance and learn the contents of all of the buckets during the attack? Does that help the attacker to come up with better attacks? Okay, so in our paper, we developed 4 different models, and these are actually really closely based on models that we found in the literature from previous work looking at cardinality manipulation and other properties of HyperLogLog. So we end up with 4 different scenarios. In the first scenario, S1, this was introduced by Revi and Ting. They assumed that the adversary is able to interact with a shadow device that performs exactly the same way as the target device, the target HyperLogLog instance, but otherwise has no information, so doesn't know the hash function, etc., etc. We're actually going to take, I'm going to take this scenario off the table for the rest of the discussion today. We think it's actually a pretty unrealistic scenario to consider attacking a cardinality estimator in. And what you notice then is that S2, S3, S4 become progressively stronger. There are more and more ticks, so the adversary is always able to insert items, obviously, in each of S1 up to S4. In S2, S3, S4, we assume that the parameters of the HyperLogLog instance are known. And then in S3 and S4, we allow getting cardinality estimates. And finally, in S4, we allow the adversary to get a snapshot, by which I mean the adversary is able to learn the contents of all of the buckets during the execution of an attack. So here you see that S4 has all ticks, and that makes it the strongest attack scenario for the adversary. Here the adversary has the most power. So we look at attacks in these different settings. Setting S1 is actually pretty challenging to do attacks in. And so there the attacks are the most interesting cryptographically. But I really want to focus on attacks in S2 through S4 in the rest of this talk. So here's a fundamental lemma that we use in our analysis of HyperLogLog. So we're going to start with a HyperLogLog instance which is initially empty, and we're going to allow the adversary to insert elements X from some set big X. And let's suppose the adversary can guarantee that it only will hit some subset of all of the buckets. So when the hash values are computed, we're only going to end up inspecting at any point some number B out of all of the M buckets that are available. And here we assume that B is less than some value B max, given by this expression. B max is this complicated expression here. Then what we can show is that at the end of the attack, no matter how the buckets are filled, as long as we only touch some maximum number B of the buckets, the cardinality estimate will be bounded in this way: M times log of M over V, where V is equal to M minus B. M is the total number of buckets, and B is the number of buckets that we inserted things into. So M minus B is the number of remaining empty buckets at the end of the attack. So just to explain these terms, the last term here, because L is typically large, is approximately 1. So it's 1 minus 2 to the minus something of medium size, then inverted. So that's about 1. The term here is approximately 0.7. And that's because of the choice of alpha M in the definition. That's that constant that's used to adjust the cardinality estimates. And so what we're really getting here is, if you look at what's going on, this cardinality estimate is coming from the small range correction case. So what we're really saying in this lemma is that as long as you don't touch too many buckets, the cardinality estimate will always stay in the small range correction part of the final processing of the estimate. So the takeaway here is that because of this factor here that's 0.71 and this factor that's approximately 1, an adversary can actually insert things, can hit about 71% of the buckets with any values it likes, with any values mj, so the number of leading bits is irrelevant, but still stay within the small correction zone. So this formula here will be used for calculating the cardinality estimates. So this is just based on analyzing the exact behavior of the HyperLogLog algorithm. What does it mean? Well, suppose we set b equals m over 2. Remember, that's like, that's 0.5 m, and we're allowed to use up to about 0.7 m. Then when you analyze, what you can do is, what this means is that the attacker can hit about half of the buckets, which means it can expect to insert about half of all of its inputs that it might have, and still keep the cardinality estimate all the way down to 0.693 times m, where here m is the number of buckets. So m, remember, was 2 to the n, where n lay between 4 and 16. Okay, what that means is that we're getting a pretty small cardinality estimate. It's linear in the number of buckets. It's, below the number of buckets, even though the adversary is inserting up to half of all of the items. So the amount of selectivity that we need here is rather small, meaning the adversary can insert into the HyperLogLog estimator almost every second item that it might want to insert. Okay, so we can almost insert an arbitrarily large number of items, and the cardinality estimate will not get too big. Similarly, if we set b equals 1, then what that means is we're only ever going to hit one bucket. We have m buckets in total, so we expect to be able to insert a fraction about 1 over m of all inputs, right? Because each time the bucket that's being selected could be one of m possibilities, and we're saying we only want to hit one of the buckets. But if you do that, you can show that this cardinality estimate back here in the lemma, this formula here, m times log m over v, actually gives you the value 1. Okay, so we can insert a fraction, maybe 1 and 2 to the 16 of all inputs. That could still be very many inputs. It could still be 2 to the 20, 2 to the 30 inputs, take your pick. But the cardinality estimate will never go above 1. So the HyperLogLog estimator will believe it has only seen one item in the set, despite the fact that you've given it, it's actually seen many, many values, very many inputs. So the sort of takeaway is that in scenario S2, an adversary can insert some fraction of all possible inputs and still keep the cardinality estimate to a constant, even down to 1. You can do even stronger attacks in S4, and there are variant attacks if the HyperLogLog instance was already partially filled with honestly selected inputs. So I'm not going to talk about those variant attacks here. I just wanted to give you a flavor of how easy it is to exploit HyperLogLog. Okay, oh, and of course, yeah, we implemented the attacks and they work. You might wonder about variants of HyperLogLog that are used in practice. In practice, HyperLogLog might be implemented slightly differently. So in Redis, for example, this estimator is used. Okay, we still have this constant times m squared, but now it's divided by some other completely different formula here. Okay, so there's some function sigma, some function tau. It doesn't really matter what those are. It's just to illustrate that there are different ways of potentially computing the final cardinality estimate. We analyzed and broke the Redis implementation as well. So it turns out that by carefully analyzing the denominator here, you can control the value of lambda hat again and keep it small while selectively inputting values. Okay, so what about repairing HyperLogLog? Well, it turns out that, so this is like, how can we fix the situation? What can we do? In S1, actually, the attacks they really don't care about the internals of the implementation. So it seems like there isn't really any repair to HyperLogLog that we could do. There's nothing cryptographic that we can do, for example. And we actually have quite strong attacks in the setting, but actually the setting doesn't really make that much practical sense. The only reason we considered it was because people had considered it in prior work. So we felt compelled to actually analyze that setting too. In S2, S3, S4, the other attack settings, which get progressively stronger, there is some hope. And so what we can do is consider replacing the hash function h with a keyed pseudorandom function, a PRF, which I denote as f of k comma dot, where dot represents the input. And here we assume that key k is going to be unknown to the adversary, even if the adversary learns the internals of the HyperLogLog instance. So we're in a secret key setting, and we assume that the key k is never compromised. Okay, so what we're doing is saying, really, can we use cryptography and simple symmetric key cryptography to help us rescue the situation for HyperLogLog? So let's consider replacing h with a pseudorandom function. And the idea is that if the adversary doesn't know the key k, then the outputs of the pseudorandom function look just like random values as far as the adversary is concerned. And so the intuition is that the adversary really is reduced to the ideal or the random input case in this setting. And in that average or ideal or random input case, we know that the adversary cannot really influence the cardinality estimate in a bad way. All that's happening is that instead of the adversary being able to use a controlled value h of x, say, we're going to replace those values h of x with some pseudo-random value that the adversary doesn't even necessarily get to see in its attack. And it certainly can't predict the value of f of k if f is a good pseudo-random function. Okay, so the question is, how do you formalize this situation and actually get something rigorous? And here's where things start to get a little bit complicated. So we introduced a simulation-based security model for analyzing HyperLogLog. So like all simulation-based security models, we have a real-world adversary and we have an ideal world adversary. So here's our adversary, A, and it's interacting with an instance of HyperLogLog, which is now using a pseudorandom function f instead of a hash function h. So the HLL f is just meant to denote our updated instance of HyperLogLog, now using a PRF. The adversary is able to interact with this instance using multiple different kinds of queries. So you can initialize it, you can insert values, you can read the cardinality estimate back. So you can ask for the cardinality estimate, and the adversary finally can corrupt the HyperLogLog instance and learn all of the internal values, in particular, the values in all of the buckets. So these arrows are just meant to represent forwards and backwards that the adversary is interacting with the HyperLogLog instance. And at the end of its execution, the adversary outputs some output A. So that's the real world. It's just the adversary directly interacting with the HyperLogLog instance, but now using a PRF. In the ideal world, we have now the adversary is actually now being run as a subroutine by a simulator. Okay, and so now the simulator is going to handle all of the queries made by the adversary, but we're going to put some restrictions on the simulator. In particular, our simulator is restricted to handling all of the insertion queries by using random sampling. So in the real world, the insertion queries are handled by computing y, evaluated using the pseudorandom function with the hidden key k on the input x. And this value y is then split into two parts. One part identifies the bucket, and the second part identifies the value that's to be updated. What we're saying here is that our simulator is going to be required to not use a pseudorandom function, but just for each distinct value x, sample a fresh random value y, and use that to perform the insertion. And what that means intuitively is that our simulator S is forced to provide a simulation of the HyperLogLog instance that's really in the average case or in the non-adversarial setting, because these y's are just uniformly random values, which are actually no longer under the control of the adversary. The adversary gets to select x, but x has no bearing on the value y, which is actually used to update the HyperLogLog instance. And then finally, at the end of the game, the adversary outputs some output A again, and our simulator is forced to copy that output. So this is another restriction on our simulator, that it should output whatever A outputs as its final output. So we have these two worlds, and what we demand is that for every adversary A, there exists, actually, it's the other way around, there exists a simulator such that for every adversary A, these two views, these two outputs are computationally indistinguishable. What that means is that there's no efficient distinguisher that can distinguish between the output produced by A when it's interacting in the real world with a real instance of HyperLogLog using a pseudo-random function, and the output of A, or the simulator, when adversary is interacting with a simulator, which is actually just really acting in the average case or in the non-adversarial setting. So security says there exists a restricted simulator S with these restrictions in orange on the right-hand side, such that for all adversaries A, these two outputs are computationally indistinguishable. Okay, any questions about this security model? You might be wondering, why does this tell us anything about cardinality manipulation? Why does satisfying this security definition that these two outputs be computationally indistinguishable tell us anything at all about the security of the scheme of HyperLogLog using a PRF against cardinality manipulation attacks? Let me try to give you an insight as to why that's the case. So in the ideal world, as we said, the simulator is forced to handle the insertion queries in a non-adversarial way. For each distinct X, a fresh random Y is actually processed. So in a very strong sense, the adversary really has no influence over how HyperLogLog behaves. It's as if HyperLogLog is operating in the truly random setting, where the inputs are really out of the control of the adversary. Okay, so yeah, S is actually running A in a non-adversarial or average case setting. In the real world, at the end of its execution, A's output might actually be a cardinality estimate, because A is able to make a read query at the end of its execution and then output that value that it gets from a read query as its final output. So remember, read queries tell A the current cardinality estimate being made by the HyperLogLog instance. So here, A, you can have many different A's, but there are specific A's that just output a cardinality estimate at the end of their execution. So, okay, the next step in the argumentation is to say, well, in the ideal world, S would also output a cardinality estimate, because S outputs in the ideal world whatever A outputs in the ideal world. But the cardinality estimate in the ideal world is a non-adversarial one because of the restrictions that we placed on S. So remember, S is always forced to insert random values. So whatever cardinality estimate A gets from interacting with the simulator in the ideal world, it's not going to be influenced in any way by A's behavior. It will be a good or non-adversarial cardinality estimate. But the security definition says that this cardinality estimate has to be close to the cardinality estimate that A outputs in the real world, because we require the two output distributions to be computationally indistinguishable. So the real world output of A must be close to a non-adversarial cardinality estimate. It's precisely the one that was output by S in the ideal world. Okay, so we didn't start out trying to say anything about cardinality estimates, but because of the generality of the model that we have here, and the fact that we allow any outputs at all, including cardinality estimates as the output, we're able to show, and also because of the restrictions on the simulator, that essentially the simulator has to provide a simulation for A, which is in a non-adversarial setting, we're able to show then that this security definition prevents cardinality manipulation attacks. So there's quite a lot going on there, and it took us a long time to come up with this way of thinking about security for analyzing HyperLogLog. And actually, the security definition is very powerful because it doesn't just capture cardinality estimation manipulation; it captures anything bad that the adversary might try to do to our HyperLogLog instance. So overestimation, underestimation, whatever you can think of is covered by this model effectively. So the formal security theorem that we have in the end says that with the simulator, as described above, if we have an adversary against HyperLogLog using a pseudorandom function, then for any distinguisher D, we can construct a PRF adversary B against the pseudorandom function, where the advantage of the adversary against the pseudorandom function is the same as the advantage of the distinguisher in distinguishing the real world from the ideal world. So the intuition here is that, well, if we're using a good pseudorandom function, then this advantage here must be small, Okay, and therefore the advantage of any adversary, not just B, against the PRF must be small, and therefore this advantage term on the right-hand side must be small. In other words, there is no good distinguisher distinguishing the real world from the ideal world. So in essence, what we have is a security reduction down to PRF security of the pseudorandom function f. And that's really what these few things are saying here. And we also account very precisely for the resources. So the number of queries that B would make to its real or random PRF oracle is the same as the number of queries that A makes to its insert oracle, for example. And we can also account for running times. So this is the usual way that we prove concrete security theorems. We prove a reduction, or we relate the advantage of an attacker against the scheme that we want to analyze. Here, the HyperLogLog using a pseudorandom function scheme to the advantage of some other adversary. And then we say, well, no such adversary can exist because f is a good pseudorandom function, and therefore we get security. And we get it in a very concrete way through this theorem. So how should we instantiate the pseudorandom function in order to actually use this thing in practice? What we want is a short input pseudorandom function that's as fast as possible. In particular, we want it to be as fast as non-cryptographic hash functions like murmur3, which are typically used in current implementations of HyperLogLog. The solution is to use something called SIP-hash, which was designed by Almason and Bernstein. It's got hash in the name, but it's not really a hash function. It's actually a pseudorandom function, plausibly a pseudorandom function. It's been cryptanalyzed to some extent and has stood up quite well. And it's actually extremely fast. So it's only a little bit slower. It's about 40% slower than the murmur3 hash function, which is a non-cryptographic hash function on 90-byte inputs. I'm not really sure why we chose 90-byte inputs here. I guess we just chose some round number or relatively round number to analyze the speed of these operations. In contrast, you can see that the PRF built from HMAC using SHA-256 takes about 7 times as long, or maybe even longer, maybe 12 times as long as murmur3. So by using this specially designed pseudorandom function, we don't lose too much performance for our HyperLogLog device or instance compared to the non-secure version. Okay, so I think we're very short of time, so I think maybe I will skip the second focus altogether. Maybe I will just jump to the very last slide to say that we, in some recent work, let me just skip through these slides on Bloom filters and so on, and just say that we have recently extended this real-world, ideal world, or simulation-based approach that we introduced for cardinality estimators to study approximate membership query probabilistic data structures. So think of Bloom filters and cuckoo filters as being the kind of canonical instances of AMQ PDS. And it's a very similar flavor with slightly different results. And the key takeaway is that if we replace the hash functions used in these PDSs by pseudorandom functions, and we're willing to spend a factor of 2 or 3 additional storage, then we can gain adversarial correctness for Bloom and cuckoo filters. An interesting bonus is that our approach enables us to address privacy as well as adversarial correctness for these AMQ PDS. And maybe that's not so surprising because these simulation-based security models were originally introduced in order to prove things about privacy or confidentiality properties. Think about semantic security for public key or symmetric encryption. There is really a simulation-based security model that's used. So we're able to kind of kill 2 birds with 1 stone. We're able to study privacy as well as adversarial correctness. And I just wanted to mention this is joint work with Mia Filic, Fernando Virdia from Royal Holloway, who's joined me as a postdoc, and Anupama Unnikrishnan, who's a postdoc in my group. And there's a paper in submission that we've written about this. If you're interested, feel free to email me and ask me for a preprint afterwards. So just to close, I think probabilistic data structure are a really fascinating branch of theoretical computer science. I didn't know much about them until recently. I'm learning a lot. It turns out that they are widely used in practice in different kinds of scenarios with many different variants. And deployments can be vulnerable to attacks of different kinds with different levels of severity as well, as we saw at the beginning of the talk. We've got the beginnings now of a general theory of secure probabilistic data structures. It's not only our work, there's some very nice work done by Clayton et al., published at CCS a few years ago. And earlier than that, a paper that appeared at, I think, Crypto 2015, which looked at Bloom filters. And they were all using game-based security definitions. Here we're using simulation-based definitions, and I think they're more powerful and more flexible. Final remark is that if we start with security in mind, we might actually arrive at completely different designs for our probabilistic data structures. So all PDS up until now have been designed really without thinking about adversarial environments, at least not in a very systematic way. Now that we come from a kind of cryptography/security perspective to this problem, maybe we'll end up with completely different designs for our probabilistic data structures, thinking as security being a first-class concern for these data structures. Good. There's a few thanks here. So I talked with Paul Grubbs a lot about these ideas. Karin Holzhauser in my group a couple of years ago did a very nice bachelor's thesis looking at cascaded Bloom filters. Mathilde, my co-author, and also my other co-authors at ETH now. I discussed quite a lot with Tom Shrimpton. And finally, Microsoft Research have set up a research project with us to investigate this whole topic further. And their funding is being used to support Mia Filic, who is a PhD student in my group. So that's everything from me. I'd be very happy to have your feedback or your questions at this point. Thanks very much for your attention.
Thank you, Kenny. So yeah, that's just one comment to start with. I have been working on probabilistic data structures in security for some years, and I totally agree what you said in the conclusion. Yeah.
I'm very sorry, I wasn't aware of your work, Changyu.
Right. So yeah, in the past we have used Bloom filters in private settings section. And last year we had a paper in Unix which used FM Sketch, which is also a cardinality estimator for cardinality estimation essentially. But we also found if we use a key pseudo-random function was keyed hash instead of public hash, then we might get we can get differential privacy for free from the.
Oh, that sounds very interesting. Yeah. Great. So I'll go look for those papers. Yeah, I didn't really mention this, but there's a long tradition of using probabilistic data structures in kind of more complex cryptographic constructions, but not necessarily thinking about adversarially chosen inputs to those constructions. But it sounds like the last piece of work you were talking about is of that type, right? Mm-hmm. Okay, good. I will take a look at that and see how we should cite it in the papers that we're writing. Sounds really interesting.
Yeah. So let's see if we have questions from the audience.
I think people can maybe just unmute. I don't know what you normally do in these seminars.
Yeah, usually they just ask.
Okay. Yeah.
Kenny, it's a little, oh, sorry, I didn't mean to jump in.
Go ahead, Elizabeth.
It's Liz. Hi, thank you for the great talk. I was wondering, at the very beginning, we were talking about HLL. You talked about some formal results, but then I assume that had nothing to do with security. It was just a question of what they managed, what the system managed to achieve, because you had to come up with this new with the simulation-based definitions, because nothing existed before, no analysis existed before. Is that correct? That
is correct. There was some analysis of attacks. So I mentioned two papers, but there was no formal security analysis of any kind for HyperLogLog or cardinality estimation that I was aware of.
And this idea of restricting. Oh, sorry.
I was just going to say there was this previous work by Clayton et al., including Tom Shrimpton, but they were more focused on things like Bloom filters and related objects rather than cardinality estimation.
Yeah. And the restriction of the simulator, is that something that you've seen before? Is that something special for this?
I'm glad you asked me about that. So that's a really strange feature. So normally in these simulation-based security models, you might restrict the adversary's input, for example. So for example, if you're dealing with, what's it called, confidentiality, you would insist that the adversary's messages all have the same length or something, or his pairs of messages have the same length. And the simulator we'd be given the length of the message so that it can simulate encryption properly. But here we restrict the simulator rather than the input to the simulator. And so, yeah, I think that's a novel angle. And I think people who are used to simulation-based security models have a hard time getting their head around that change, that we're actually restricting the simulator rather than the input to the simulator. Yeah, sorry, I was trying to remember semantic security makes that restriction. So yeah, it took us quite a long time to arrive at that kind of understanding of that's the way to handle this thing. So you basically, in the ideal world, the adversary is really interacting with a simulator, which is providing a kind of average case simulation of HyperLogLog, in which case the adversary can't really do very much.
I wonder how would that translate in more traditional settings, like if you restrict simulators, what result? Yeah, it's quite an interesting approach.
Yeah, it's a good question. Yeah, I'm not completely sure. Indeed.
Thanks.
You're welcome. Thanks for the question.
Yeah, so so the HLL algorithm that you showed earlier, actually, I don't remember it fully, but was there anything probabilistic about that algorithm?
Oh gosh, that's a great question. So actually, so let me just bring it back up again so we can see it. And if I can do a slideshow from here, you should be able to see it again. Can you see that now?
No, right now, no.
No? Okay, maybe I'm not screen sharing then. Hang on. Let me do that. Oh yeah, I see what I did wrong. Okay. After all this time, I'm still not very good at running Zoom. Okay, and now I do. No. Okay, hopefully you can see that now.
Yes, I can see that now.
Yeah, you're absolutely correct. There's nothing probabilistic about this, except that implicitly there's an assumption that the hash function is a random oracle.
Ah, I see.
Right, and if you look very carefully at the security, not the security analysis, just the performance analysis in the paper by Flajolet et al. From 2007, they kind of assume, without really explicitly stating it, that H behaves like a random function. So that as long as the inputs are distinct, the HyperLogLog estimator is really getting random values Y out of this hash function H of X here. So for distinct X's, you get uniformly random outputs. And of course, for a fixed hash function, that's not true, right? And so all of the instantiations, all of the implementations of HyperLogLog replace this random oracle with a fixed hash function, and then they're vulnerable to attack.
Yes.
Yeah. So it's sort of probabilistic, but it's not obviously probabilistic on the surface.
I see. So
Yeah.
I'm just wondering, does the correctness of this algorithm actually relies, in some intricate way on the properties of the hash function? The reason why I'm asking this is because you have a drop-in replacement of this hash function with the PRF,
Right.
and I wonder they satisfy the same properties that the algorithm relies on.
I see. Yeah. That's also a very nice question. So if you think about it, one more comment about your previous remark first. The probabilistic and probabilistic data structures doesn't necessarily refer to the data structure being a probabilistic algorithm. It's that it gives answers that are probabilistically correct.
Right?
I see.
Okay.
So it's more about it, the probabilistic part more refers to the quality of the output rather than the operation of the algorithm itself. So for example, Bloom filters are also deterministic, but they have false positives, and so they only give you probabilistically the correct answers to membership queries.
Okay. Yeah.
Now to your question about what do we need of the hash function. So again, the average case analysis in Flajolet et al. Really just assumes that H is a random function. If we replace H by a pseudo-random function, then as part of the security analysis, you're actually replacing a PRF with a random function in the security analysis. And so you end up in the same place where the original analysis of Flajolet et al. Takes place.
All right.
Yeah.
Because the only property it relies on is it being a random. So
exactly.
Uniformly random.
Yeah. And it's safe to replace the PRF with a random function Otherwise, you could build a distinguisher for the PRF, right? You'd be violating the PRF security property.
Right. Yeah, makes sense. Thank you.
Thanks a lot for the question. Thanks.
Okay.
I don't know whether, I don't know whether my hands was coming first or not. I was waiting for the gap.
Yeah, you were first, Li-Chun. Yeah, go ahead.
Yeah, thank you for your talk. I have to apologize. I joined your presentation only halfway because I have other meetings. I probably missed the bit you already said for the answer my question. In the last work you mentioned, your work including both privacy and adversarial environment. I'd like to ask about privacy.
Sure.
What do you actually mean privacy? Is just the data privacy because data is hidden in those filters and it's splitted like zero knowledge? Or you actually means more than that, like the entity privacy for who is involved and so what is that?
So it's really a confidentiality property. It says something along the lines of an attacker can't infer values that are in the Bloom filter other than by making the right queries to the Bloom filter and observing that they are recorded in the Bloom filter. If you give the adversary an API using which it can query the Bloom filter, you can't stop it from doing that attack. But what we prove is it can't do any attack better than that. So in particular, if your input was from a very small set that was hard to guess, then our result would show the adversary was not able to guess values in the Bloom filter, for example. Now, is that really privacy? Maybe not. It's not kind of like privacy in terms of personal information, say, but it could translate to that depending on the application.
Dependent on your data set, how big is it?
Exactly.
Yeah. Recently, I see some interesting comments about GDPR. It's nothing to do with this work. That people interpret GDPR, say if the data is hashed, you cannot claim GDPR, say you protect the data because this is not confidentiality.
Oh, I see.
And then people said, if the data is encrypted, then no matter whether it's the hash or not hash, you actually pass GDPR. I thought that the answer should be yes, but actually the answer is no from what the GDPR experts' interpretation. Because they say that if you put the ciphertext in public domain and the encryption algorithms or keys, they are not long-term secure. Eventually it will be broken, so it's still not GDPR associated. So that's why privacy, data privacy is actually more tricky than what we understand.
Great.
Yeah. So this is not a question to you, but if you like to comment,
well, I have no expertise whatsoever on GDPR, and so I'm very happy to get that information about what GDPR says about cryptography. It's very interesting. I
don't think GDPR say cryptography, but the GDPR interpreter can explain anything, including cryptography. They don't think it's strong. So for the technology you are used, seems from different angle to say data privacy.
Can I add comments?
Sure.
About GDPR? Sometimes, right, they say if it's encrypted, it's still not private because eventually encryption can be broken.
Yeah.
But sometimes they just accept weaker privacy definitions like k-anonymity or just throw away the identities. And they say after you do that, the data is private. That sounds really
it's bizarre. Yeah, it's not quite balanced. Okay, thank you.
Thanks, Li-Chun. Nice to see you too.
Nice to see you.
I think Siamak had a question, maybe.
Yeah, I don't know if we are already over time, so I don't know if you have time to discuss.
I can hang on for maybe one or 2 minutes more. I actually have to go to a departmental meeting.
Sure. I was just wondering if you could give a bit more sort of intuition about why you chose in the security model, why you left it open for the adversary to output anything, because this covers basically sort of anything that the adversary can learn from any of those oracles that they have at their disposal, right? So
yeah.
Is that what your thinking was, or was it something else at play?
That's a really interesting question. So I can tell you that for HyperLogLog, it was really my first time properly using simulation-based security definitions. So really, in that case, I was more kind of copying from the literature and then interpreting that, oh, the output could be a cardinality estimate, therefore we can't distinguish. And so that enables us to achieve the objective of proving that cardinality manipulation cannot be done by the adversary. But then actually in the follow-up work that I mentioned only very, very briefly at the end, where we look at AMQPDS, it turns out there that this kind of generality is very useful, because there's many different ways that you might want to try to manipulate an AMQPDS. For example, you might want to do pollution attacks where certain inputs become marked as false positives, even though they've never been input. Like you might want to target, google.com as a domain in a Bloom filter that's covering many domains.
Sure.
And then you might also want an attacker to be able to, maybe the attacker's objective is to create more false positives than you would expect to get, given the load on the Bloom filter. That would be a different attack objective. And it turns out this general approach that we have of indistinguishability of real and ideal worlds covers all of those things.
Sure.
All you have to do is change what the adversary is doing at the end, what it outputs. And then for free, you get all of these different security properties. However, we get those security properties with slightly weaker bounds than you could get if you analyzed each security property individually.
I see.
So there's a win and there's also a loss. So in the paper by Clayton et al. From CCS, they analyzed Bloom filters and they proved bounds that are slightly tighter than ours in certain regimes. But they only looked at one, it was a game-based approach, and they only looked at one winning condition, which was the adversary should produce at least R false positives for some parameter R. And so, because we don't work at that level of detail and we don't pick a specific value of R, we don't get a bound that's as sharp as their bound would be. So you win something and you lose something, but in the end, it gives you something quite powerful, actually, I think.
Is composability also a possible win, or is that going too far?
No, it absolutely is. The problem there is I know almost nothing about composability. I know a little bit about UC and so on, and I know that some of these definitions can be composable. That's not something we've explored, but it definitely is another plus point that we don't emphasize very much, because we're not really thinking about using these as part of some larger secure system, but maybe just kind of as a standalone thing at the moment.
Sure. Thank you.
Definitely in future, that could be a useful perspective. Thanks. Great questions.
Can I have a very quick question?
Please.
Yeah, I wonder whether the distinguishability property, the probability of distinguish the real and the simulation game can be zero, such that it is perfectly hiding, for example.
Not in the constructions that we have using pseudorandom functions. So I'm trying to think now. I'm not sure. I mean, obviously getting to zero would be great, because then you would have like a, absolute perfect equality between the two views. But I think there are, I'm just thinking now, for HyperLogLog, it might be possible to achieve that. But for something like Bloom filters, maybe not. I think it's always possible to, no, actually, I'm really not sure. Yeah, it's an interesting question. Thanks.
Thank you.
Thank you. Unfortunately, I should go, because I need to go to my department's meeting of professors and talk to some professors. So maybe I'll hand back to Chang Yu for the final word.
Right. Yeah. Yeah. Thank you very much, Kenny, for the interesting talk. And I guess you have seen people are engaging to the topic very much. And thank again, and hope later if anyone has questions or any interest about Kenny's work, send the email to him, and maybe a collaboration can be formed.
Perfect. I'd be very happy to hear from people. Thank you so much for the invitation.
Okay. Thank you. And now we can conclude this session.
Thank you.
Yeah.
Thank you. Bye. Nice to see you all. Bye-bye. Bye.